June 13th, 1944. London, England. Just 1 week after the hope of D-Day, a new kind of terror arrived in the sky. It wasn't a plane, but a pilotless bomb with a sputtering engine that created a sound of pure dread. The V-1 doodlebug was fast, low, and a weapon of indiscriminate horror. Britain's vaunted anti-aircraft guns were helpless against it, with a hit rate of less than 1%. With the city defenseless, this became the story of how one civilian's impossible invention, an electric brain from the telephone company, let U.S. guns obliterate Hitler's V-1 flying bombs. In the early hours of June 13th, 1944, the war for Europe had reached a fever pitch. Allied forces were still fighting tooth and nail to secure their foothold in Normandy, just 1 week after the D-Day landings. It was a moment of fragile hope. And then, a new kind of horror arrived. It came from the Pas-de-Calais region of France, a strange, stubby-winged aircraft that flew without a pilot, a strange stovepipe contraption strapped to its back. From this pipe erupted a deafening, rhythmic roar, a sound so unnatural and menacing it would forever be seared into the memory of those who heard it. This was the Fieseler F-103, better known as the V-1. The V stood for Vergeltungswaffe, the vengeance weapon. It was a direct response to the Allied bombing campaigns that had been pummeling German cities. It was the world's first operational cruise missile, a simple but brutally effective weapon of terror. Its pulse jet engine, a masterpiece of minimalist engineering, burned low-grade gasoline to produce about 600 pounds of thrust. The engine operated by taking in air, igniting fuel, and blasting out hot gas in a rapid series of explosions, about 50 times per second. This rapid-fire combustion gave the V-1 its signature, terrifying sound, a low, guttural pulse that earned it a host of nicknames from the beleaguered British public. The buzz bomb, the doodlebug, the cherry stone. For the citizens of London, that sound became the soundtrack of their deepest fears. It was a constant, nerve-shredding presence. Windows would rattle, teacups would tremble on their saucers. People would stop in the street, heads cocked, listening to the approaching drone. As long as you could hear the buzzing, you were paradoxically safe. It meant the bomb was still under power, still flying, still on its way to someone else. The true heart-stopping terror began in the moment of absolute silence. A small propeller on the V-1's nose was set to spin a specific number of times, roughly corresponding to the distance to London. Once it hit its count, it would cut the fuel lines and lock the elevators, pitching the drone into a steep, silent dive. From that sudden cessation of noise, from that chilling silence, people on the ground had between 10 and 20 seconds to find any cover they could: a doorway, a ditch, a descent into a cramped Anderson shelter in the backyard. Then came the explosion. Its nearly 2,000-pound Amatol warhead was potent enough to flatten entire rows of houses, to turn brick and mortar into a cloud of dust and splinters. The psychological toll was immense, precisely as its designers intended. This was a weapon of indiscriminate horror, a lottery of destruction. It didn't aim for military targets. It aimed for a city. It was designed not just to destroy buildings, but to shatter the morale of an entire nation. Over the next 88 days, a relentless stream of these vengeance weapons flew across the Channel. More than 9,500 were launched at England, with thousands more targeting the vital port of Antwerp in Belgium after its liberation. They came at all hours, day and night, in sunshine and in rain. They were fast, reaching speeds of up to 400 miles per hour in a slight dive, and they flew low, typically between 2,000 and 3,000 feet, an altitude that made them nightmarishly difficult targets for the defenses of the day. More troubling than the weapon itself was the sheer, galling ineffectiveness of those defenses. The Royal Air Force scrambled its fastest fighters. The Hawker Tempest and the newer models of the Spitfire were among the few planes that could catch a V-1 in level flight. But it was a dangerous chase. Pilots quickly learned that shooting one at close range was a form of self-destruction. The massive warhead would detonate with enough force to rip the wings off their own aircraft. An even more daring tactic was developed. Pilots would fly alongside the buzz bomb, slide their wingtip just under the V-1's stubby wing, and then gently but firmly lift up. This would tumble the drone's primitive gyroscope guidance system, sending the missile spiraling harmlessly into the countryside. But this was an act of incredible skill and bravery, a desperate measure, not a sustainable defense against a swarm of thousands. The primary defense fell to the massive ring of anti-aircraft batteries positioned around London. But these guns, and the men who operated them, were facing an impossible, soul-crushing task. Their targeting systems, complex clockwork computers called predictors, were designed to track the slower, high-altitude heavy bombers of the Luftwaffe. They were utterly confounded by the V-1's speed and low-altitude approach. Gunners were essentially firing blind, throwing up a barrage of shells in the vague hope of a lucky hit. The initial results of this defense were catastrophic. In the first week of the V-1 Blitz, Anti-Aircraft Command fired over 24,000 heavy-caliber shells. They managed to bring down only 177 buzz bombs. That is a staggering 135 shells for every single success. By some internal military estimates, the hit rate was as low as one hit for every 5,000 shells fired. The defense was a failure. The impossible was becoming a daily, deadly routine, and London was bleeding. What no one in the city, in the gun pits, or even in the high command knew in that moment was that the solution was already on its way across the Atlantic. A solution born from the most unexpected of places, in the mind of a man who saw this impossible problem in a completely different way. A civilian was about to make the impossible possible. The story of the revolutionary device that would conquer the V-1 begins with a man who had never designed a weapon, who had likely never even fired a gun. His world was one of chalkboards, vacuum tubes, and the elegant language of mathematics. Hendrik Wade Bode was a scholar, not a soldier. Born in 1905 in Madison, Wisconsin, to Dutch immigrant parents, he was a quiet, intensely focused prodigy. He raced through his education, earning a bachelor's and then a master's degree in mathematics from Ohio State by the age of just 20. In 1926, with his academic credentials in hand, he joined a research and development firm that was, at the time, more focused on connecting people across continents than on waging war. Bell Telephone Laboratories. To call Bell Labs a mere company lab would be a gross understatement. In the mid-20th century, it was a cathedral of innovation, the undisputed global center of technological progress. As the research arm of the AT&T monopoly, it was lavishly funded and operated with a unique, university-like atmosphere. Its scientists and engineers were encouraged to pursue fundamental, blue-sky research, to follow their curiosity wherever it led. It was a playground for some of the brightest minds on the planet. In the decades to come, the men and women who walked its halls would invent the transistor, the laser, the solar cell, the C programming language, and the foundations of the digital age. It was into this heady, intellectual environment that Hendrik Bode arrived. Bode's early work had absolutely nothing to do with ballistics, radar, or the art of warfare. Instead, he was assigned to the Mathematical Research Group, where he became a leading specialist in electrical network theory and feedback amplifier design. His core job was to solve a fundamental problem of the telephone age. How do you send a clear human voice over hundreds and eventually thousands of miles of copper wire? A signal degrades over distance. It picks up static and loses strength. Bode's task was to design the electronic filters that could separate the pure voice signal from the hiss and crackle of unwanted noise, and the sophisticated amplifiers that could boost that signal back to its original strength without distorting it. This work was deeply mathematical and profoundly abstract. It required him to invent new ways of thinking about systems that could regulate themselves. A feedback amplifier, for instance, listens to its own output, compares it to the input, and makes instantaneous corrections. This concept of a feedback loop is a foundational principle of all modern automation. Bode became a world-renowned expert in this field, now known as control systems theory. He developed powerful graphical methods, famously known as Bode plots, that are still used by engineers today to visualize and guarantee the stability of these complex feedback circuits. To a layman, it was arcane, incomprehensible stuff. But to an engineer, it was the key to creating systems that were stable, predictable, and self-correcting. What neither Bode nor his colleagues at Bell Labs could have known was that this seemingly peaceful work on improving telephone calls was the perfect, and perhaps only, training ground for solving one of the war's most intractable military challenges. He was learning how to take a messy, noisy, corrupted input, predict what the original, clean signal was supposed to be, and then build a circuit that could automatically correct for the errors. When the United States was plunged into the Second World War after the attack on Pearl Harbor, the nation's entire scientific and industrial might was mobilized. The government established the National Defense Research Committee, NDRC, to harness the country's brainpower for the war effort. Bell Labs, with its unparalleled reservoir of talent, was given a critical and secretive role. Hendrik Bode, along with other brilliant minds like the father of information theory, Claude Shannon, was assigned to the NDRC's Section D2, which focused on a single, crucial problem: fire control. The military came to them with a challenge that seemed to have no solution. Their anti-aircraft guns were inaccurate and slow to aim. The existing systems were failing, and the threat of faster, more agile enemy aircraft was growing every day. The skepticism in the room was palpable when these telephone engineers and mathematicians were first presented with the grim realities of aerial combat. But the military was desperate. The challenge was laid down. The impossible was about to be tackled by a man who saw the world not as a battlefield of explosive forces, but as a complex series of signals, noise, and feedback loops. Hendrik Bode's mind was uniquely and unknowingly prepared for this very moment. He was about to go to war, armed not with a rifle, but with a slide rule, a deep understanding of electronics, and a revolutionary way of thinking. The telephone expert would have to figure out how to hear a whisper in a hurricane. To truly appreciate the breathtaking genius of Hendrik Bode's invention, one must first descend into the frustrating, chaotic world of early wartime electronics and mechanics. One must understand why hitting a tiny, fast-moving V-1 was a mathematical nightmare of the highest order. The story of this breakthrough is rooted in a fundamental problem of prediction, a problem that the best mechanical minds of the age had failed to solve. The 90mm anti-aircraft guns of the era were impressive pieces of mechanical engineering. They were titans of steel, capable of hurling a 24-pound shell over 37,000 feet into the sky. But a gun is a dumb instrument. It is useless if you don't know where to point it. That critical task fell to a device called a gun director. For most of the war, these directors were intricate analog computers, but their brains were made not of wires and tubes, but of gears and cams. The old system, like the Army's M2 director, was a marvel of Victorian-era clockwork precision, scaled up to solve a modern problem. It was a dense box of finely machined brass gears, spinning discs, and carefully shaped cams. To use it, gunners would frantically track the enemy aircraft through telescopes, cranking dials to feed the machine the target's estimated speed, direction, and altitude. Inside the director, this mechanical input would cause the gears to whir and click, moving the cams and levers in a complex ballet of calculation. The output was another mechanical motion, which told the gun crew the correct lead angle, the empty patch of sky where they should aim so that the shell and the target would hopefully collide several seconds later. This system worked, barely, against the slow, high-altitude bombers of the early war. But against a V-1, it was a useless antique. It was entirely dependent on human operators making visual estimates of a target moving at nearly 600 feet per second. It was slow, cumbersome, and hopelessly inaccurate. The arrival of radar should have changed everything. Radar, radio detection, and ranging was a technology that bordered on magic. For the first time in human history, defenders were not limited by the human eye. They could see through clouds, through darkness, For miles, it gave them a godlike new sense. But this new sense was imperfect. It was like getting a new pair of eyes that couldn't stop twitching. The early radar sets, like the SCR-268, could pinpoint a plane's location, but the data it produced was messy and erratic. The blip on the operator's cathode ray tube screen would jump and jitter constantly. This electronic noise came from a dozen different sources. There was atmospheric interference from solar radiation. There was electronic noise from the primitive vacuum tubes inside the radar set itself, a constant background hiss. There was mechanical noise from the vibrations of the radar antenna as it moved, and, most importantly, there was target noise. A radio wave bouncing off the vibrating metal skin of a V-1 with its pulsing engine was not a clean, neat echo. It was a smeared, distorted, and jumpy signal. Here was the fatal flaw. The mechanical directors, with their rigid gears, couldn't handle this noisy data. They would try to follow every little jump and twitch of the radar signal, interpreting each flicker of noise as a genuine change in the target's course. The result was that the aiming instructions sent to the guns were chaotic and useless. Gunners were trying to hit a target the size of a small car, moving faster than any propeller plane, and their aim point was being thrown off by dozens of feet from one second to the next. It was like trying to thread a needle during an earthquake. This is where the culture of Bell Labs became the secret weapon. The problem was taken out of the hands of the mechanics and given to the communication theorists. The challenge was reframed in a language they understood perfectly. Treat the tracking of an enemy aircraft as a communication problem. The true, smooth flight path of the V-1 was the signal you wanted to hear. The radar jitter, the atmospheric interference, the electronic hiss. All of that was just static or noise that was drowning out the signal. The goal, therefore, was not to build a better gear, but to build a better filter. In a landmark, top-secret 1944 paper, Data Smoothing and Prediction in Fire Control Systems, co-authored by Bode, Ralph Blackman, and Claude Shannon, they laid out the mathematical foundation for this new approach. They proposed using electrical networks, the very same kinds of circuits Bode had perfected for telephone lines, to smooth out the raw, jittery radar data and reveal the clean signal hidden within. But even that wasn't enough. The system had to do more than just see where the target was. It had to predict the future. An anti-aircraft shell takes time to travel. For a V-1 at a typical altitude of 2,000 feet, that flight time could be 5 to 7 seconds. In that brief window, a V-1 would travel over half a mile. The director had to calculate where the V-1 would be when the shell arrived. It needed to take the newly smoothed flight path, determine the target's velocity and acceleration, and then extrapolate that path into the future, all while simultaneously calculating the shell's own trajectory and accounting for variables like wind, air density, and the pull of gravity. The old clockwork brains were simply too slow and too stupid to perform these multiple calculus-level calculations in real time. The impossible problem required an entirely new kind of brain, one that thought not with the slow grind of gears, but with the instantaneous speed of electricity. Bode and his team were about to build a machine that could see the ghost in the radar. The revolutionary solution that emerged from the sequestered labs of Bell Labs was a nondescript gray metal box, roughly the size of a refrigerator. It had no elegant visible clockwork gears, no polished brass machinery. Peering inside, one would see a dense, bewildering jungle of over 160 vacuum tubes, dozens of complex potentiometers, self-regulating gyroscopes, and what seemed like miles of meticulously routed color-coded wiring. This was the T-10, which the U.S. Army would soon designate the M9 gun director. It was, for all intents and purposes, the world's first effective electro-analog computer dedicated to real-time fire control. The story of how it was created is a testament to a unique synergy of dreaming, mathematics, and brute force engineering. The initial spark of the idea, the conceptual seed, did not come from the mathematician Bode, but from another brilliant Bell Labs engineer named David Parkinson. In 1940, with the war in Europe raging and the U.S. on high alert, Parkinson was consumed by the problem of anti-aircraft accuracy. The pressure was immense. One night, he had a vivid dream. In the dream, he saw himself in an anti-aircraft emplacement, but instead of cranking dials, he was controlling the gun's aim using a simple device from the lab, a potentiometer. A potentiometer, familiar to anyone who has turned a volume knob on a radio, is a resistor that can produce a variable electrical voltage. Parkinson awoke with a jolt of inspiration. He realized that this fluctuating voltage could represent an angle. This electrical signal could then be used to drive powerful motors, servo mechanisms, that would aim the heavy gun automatically. He and his team hastily built a crude prototype using spare parts, proving the basic concept was viable. But turning this dream into a stable, rugged, and astonishingly accurate weapon was where Hendrik Bode's unparalleled mathematical genius was required. Bode took Parkinson's raw concept and infused it with the rigorous mathematics of control theory. The M9 director he designed was the brain of a complete, integrated weapon system. It took the raw, fluctuating electrical signals directly from a new, far more advanced radar set, the legendary SCR-584, which had its own magical ability to automatically lock onto and track a target. Inside the M9, these noisy signals were fed into Bode's meticulously designed filtering and smoothing circuits. These were not digital circuits, but analog ones. They performed calculus in real time using the physical properties of capacitors and resistors. They electronically averaged out the jitter and noise, producing a clean, stable voltage that represented the target's true position and velocity. This clean data was then passed to other circuits that acted as the predictors. Using internal, high-speed gyroscopes to establish a perfectly stable reference frame, an inner ear, so the computer always knew which way was up, the M9's analog computing elements calculated the target's future position with astonishing speed. It was a symphony of automation. For the first time, the entire aiming process was removed from the fallible hands of human operators. The radar locked onto the V-1. The M9's electric brain processed the data, calculated the future intercept point, and sent its aiming commands, azimuth and elevation, via heavy electrical cables directly to the powerful servo motors on the 90mm gun mount. The gun, weighing several tons, would slew to the correct position as if guided by an invisible hand. The gun crew's primary job was transformed. They went from being frantic calculators to being loaders. Their task was to keep the machine fed with a steady diet of high explosive shells. The system was so brilliantly holistic that it even accounted for the tiny delay between the command to fire and the shell actually leaving the barrel. The result was a true closed-loop feedback system. The radar watched the target, the computer aimed the gun, and the gun fired the shell. If the shell's burst was off target, the radar operator could see this, and the computer could make micro-corrections for the next shot. It was a system that could learn. This was a quantum leap in military technology, a jump from the mechanical age to the electronic age. The extensive tests conducted at the secret Signal Corps Radar Laboratory at Camp Murphy in Florida were stunning. When integrated with the SCR-584 radar and the 90mm guns, the M9 boosted accuracy by a staggering factor of 10 over the older mechanical systems. But it was the partnership with one final impossible invention that would make it truly unstoppable: the proximity fuse, or VT fuse. This was a tiny radio transceiver packed into the nose of each artillery shell. It constantly broadcast a radio signal and listened for the echo. When the echo became strong enough, meaning an aircraft was just yards away, it would detonate the shell automatically. A direct hit was no longer necessary. A near miss was now just as lethal. The stage was now set. The electric brain was forged. The magic bullet was ready. All that was left was to unleash this revolutionary system on an unsuspecting enemy. The impossible was about to become the inevitable. In the harsh winter of February 1944, months before the main V-1 assault on London began, The M9 gun director received its brutal baptism by fire. The new American units, equipped with the full system, were deployed to the precarious Anzio beachhead in Italy, a bloody foothold the Allies were desperately trying to maintain. The Luftwaffe threw everything they had at the beachhead, trying to dislodge the invaders. It was here that the M9, a device born in the quiet labs of New Jersey, proved its lethality. The results were nothing short of miraculous. The system, which many old-school Army officers had viewed with deep suspicion, proved its worth almost overnight. One after-action report credited the new Bell Labs director with being the key factor in downing over 100 German bombers, stunning both Allied and Axis forces with its uncanny, almost supernatural accuracy. But its true test, its legendary performance that would cement its place in history, would come that summer against the relentless buzz bombs. As the V-1 blitz on London intensified through June and July, the situation grew desperate. The city was being bled, and morale was cracking. General Frederick Pyle, the commander of Britain's anti-aircraft command, was a man under immense pressure. His guns were failing. He made a bold, career-risking decision. Convinced by the astonishing reports from Anzio, he decided to bet everything on this new American technology. He ordered a complete, radical redeployment of his forces. In a massive logistical operation codenamed Diver, he stripped the defenses from around London itself and moved hundreds of guns, both British and American, to the coast of Kent and Sussex. This created a dense, multi-layered gun belt that every single incoming V-1 would have to cross. And at the very heart of this new defensive wall were the newly arrived American 90mm batteries, equipped with the holy trinity of anti-aircraft technology: the SCR-584 radar, shells fitted with the VT proximity fuse, and the electric brain of Hendrik Bode's M9 director. The impact was immediate, and for the Germans launching the V-1s, utterly baffling. The hit rates, which had been abysmally, embarrassingly low, skyrocketed. In the first week of the new system's operation along the coast, the success rate against the doodlebugs doubled. Then it tripled. The deep skepticism among the veteran British gun crews, who had grown demoralized by their own failures, quickly turned to slack-jawed awe. They watched as these American guns, seemingly guided by a ghost, would lock onto a target, swing smoothly to a seemingly random point in the sky, fire a small burst of shells, and seconds later, a V-1 would blossom into a ball of fire. The numbers tell the story of a technological slaughter. By the first week of August, the coastal gun belt was destroying 24% of all V-1s that entered its kill zone. A week later, that number jumped to 47%. By the end of August, they were consistently destroying over 75% of all incoming buzz bombs. On the final day of the sustained V-1 assault against London, out of 104 buzz bombs detected heading for the city, an incredible 89 were shot down by the guns before they could reach their target. One American unit stationed near the vital port of Antwerp in Belgium famously took down 48 out of 75 incoming V-1s in a single engagement. In the final analysis, the victory was due to the seamless integration of these three revolutionary technologies. The radar was the all-seeing eye. The proximity fuse provided the deadly sting of a scorpion. But it was Hendrik Bode's M9 director that was the brain in the central nervous system that tied it all together. It was the director that filtered the noisy ghost in the radar and predicted the V-1's path with a precision no human could ever match. It transformed a weapon of chance and luck into a weapon of scientific certainty. The success was so total and so sudden that German intelligence was thrown into chaos. They refused to believe it was due to improved gunnery, instead suspecting that the Allies had somehow captured a V-1 intact and had engineered a radio jamming device to disrupt its guidance. They never suspected the true source was a machine that could think. Prime Minister Winston Churchill himself would later credit Bell's wizardry as a critical factor in defeating the V-1 menace. The impossible invention of a civilian telephone engineer had saved a city and forever changed the face of warfare. The relentless buzz was finally being silenced by the quiet, efficient hum of vacuum tubes. Did it really happen that way? The legacy of Hendrik Bode's achievement deserves profound emphasis, as it echoes far beyond the saved cities of London and Antwerp. The defeat of the V-1 was a pivotal moment, not just in the history of the Second World War, but in the unfolding story of technology itself. The integrated system of radar, computer, and gun effectively created the world's first successful anti-missile defense. It was a terrifyingly effective proof of concept for the automated warfare that would come to define the Cold War and the modern military era. The fundamental principles that Bode and his team perfected under the intense pressure of war, of stable feedback control, of signal filtering, of real-time prediction, have become the invisible bedrock of our technological world. These concepts are at the heart of the autopilot in every modern airliner, the guidance systems in the spacecraft that explore our solar system, the cruise control in our cars, and the complex robotics that build them. The Phalanx CIWS, the rapid-fire, radar-guided Gatling gun that acts as the last line of defense for modern naval ships against sea-skimming missiles, is a direct and clear technological descendant of Bode's electric brain. Every time a drone adjusts its flight path in a gust of wind, it is using the principles of a feedback loop that Bode helped to master. His work was a critical inflection point, the moment when warfare began its pivot from a purely human endeavor to a partnership between man and intelligent machine. After the war, Hendrik Bode returned to the familiar intellectual halls of Bell Labs. He put aside the grim calculus of destruction and went back to his true passion, the leadership of pure research. He became the head of the prestigious Mathematics Research Group and later a vice president of the entire company, guiding research into the next wave of innovations. In a fascinating and ironic twist of history, he would later be called upon to consult for the U.S. government on the Nike Zeus program, America's first ambitious attempt to build a system to shoot down intercontinental ballistic missiles. In that capacity, he found himself working with some of the very same German rocket scientists from Peenemünde who had helped create the V-weapons his invention had so effectively vanquished. For his monumental wartime contributions, he received the Presidential Certificate of Merit in 1948, one of the highest honors that can be bestowed upon a civilian. He retired from Bell Labs in 1967 and became a distinguished Gordon McKay Professor of Systems Engineering at Harvard University, teaching the theories he had pioneered to a new generation. Hendrik Wade Bode passed away in 1982. His name largely unknown to the public he helped protect, but his legacy is permanently etched into the DNA of modern electronics and automation. Now, it's fair for people watching this to step back and wonder, did it all really happen that way? Did one civilian's invention truly solve an impossible problem overnight? It sounds almost too clean, too much like a movie script. The thing is, while the M9's stunning success on the battlefield seemed like an overnight miracle, it was in truth the culmination of decades of foundational research at unique institutions like Bell Labs. Bode didn't invent the concept of feedback control out of thin air. He stood on the shoulders of giants and perfected its application under the intense, clarifying pressure of a national emergency. His unique genius was not in a single lightning strike invention, but in his ability as a systems thinker. He saw how to connect disparate, highly advanced fields, communication theory, servo mechanisms, radar, and ballistics, to create a system that was exponentially more powerful than the sum of its individual parts. It wasn't a lone invention, but a synergy of technologies, driven by the insight of a brilliant civilian mind that saw a military problem as a communications puzzle. The story is a powerful reminder that sometimes the most profound solutions, the breakthroughs that alter the course of history, come not from the generals on the battlefield, but from the quiet, persistent, and relentless pursuit of knowledge in a laboratory. The story of Hendrik Bode shows how a civilian mind can change the course of a war. But does this kind of breakthrough innovation still happen today? Or has warfare become too complex? Like and subscribe for more hidden stories of the minds that shaped our world.